Space travel, the final frontier. It's quite the interesting endeavor, and we often hear about its successes and failures. Today, let's dive into the physics and mathematics behind making space travel a reality. Specifically, we'll examine Kepler's three laws and how they relate to orbits, and then derive the Vis-Viva and Rocket equations. In doing so, we'll figure out how to get from this to this. The material covered in this video is a summary of the fundamental mathematics used by aerospace engineers and rocket scientists to determine the exact spacecraft and orbital parameters required to complete the mission. Calculus is an integral part of these calculations, as it gives us the ability to derive and model complex formulas while maintaining a high degree of accuracy. Without it, many calculations would have been near, if not completely, impossible. So yes, at the end of this video, you'll be able to say that you did some rocket science today.
Orbits. They come in many shapes and sizes, widths and lengths, eccentricities and inclinations. However, as per our friend Johannes Kepler and his first law, we know that the orbit of a planet is an ellipse with the sun at one focus. This law also applies to satellites in orbit around the Earth. But what's a focus? Well, an ellipse actually has two foci, which are 2 points whose sum of distance from any point on the ellipse is always the same. For example, if we have our blue and red foci and we draw straight lines from both of them to a point on the ellipse, and then we draw another pair of lines to another point on the ellipse, right over here. The sum of the first blue and red lines is equal to the sum of the second pair. Going further down the orbital parameter rabbit hole, we discover that essentially every elliptical orbit has something called a semimajor axis and a semi-minor axis. Essentially, the semimajor axis is the line which originates in the center of the ellipse, intercepts one of the foci, and goes to the edge of the ellipse at its widest or longest point, so this diameter over here. On the other hand, the semi-minor axis is a straight line from the center of the ellipse to the ellipse's edge at its tightest point, or kind of relative to the center, so this diameter over here. From this, we get a pretty nifty formula which allows us to calculate the eccentricity, or how much the ellipse deviates from being a circle, given that we know A, the semi-major axis, and B, the semi-minor axis. Subsequently, using this formula, we know that the eccentricity of this right here is 0, since it is a perfect circle. We know that the eccentricity of this one over here is 0.866, and subsequently we have an eccentricity of 0.917. What's also interesting is that while an eccentricity of 0 means that it is a perfect circle, an eccentricity of 1 is essentially a straight line with 100% deviation from being an actual circle. This brings us to Kepler's second law, which is that a line segment joining a planet and the sun sweeps out equal areas during equal intervals of time. Specifically, if we have the Earth at the white focus, and let's say a satellite is in the displayed orbit over here, then if it travels the highlighted distance in 30 seconds, then the area of this triangle will be equal to the area of the triangle produced by the satellite traveling at the other side of the orbit in 30 seconds. So these two highlighted areas are actually equal. Finally, we arrive at Kepler's third law, which states that the square of the orbital period of a planet is proportional to the cube of the semi-major axis of the orbit. We'll get into this formula a bit later, but keep this in mind as we'll be using it to determine the relationship and derive a pretty important equation later on. So, now that we've got a basic understanding of how orbits and orbital parameters work, however, as you can see by the diagram on the left over here, the terminology surrounding them gets pretty wild. So let's focus on what we need to know to complete the task at hand. These are really the semi-major axis, which we have already discussed, the apoapsis, which is the highest point in the orbit, the periapsis, which is the lowest point of an orbit, the period, so how long it takes the object to go around its orbit, the universal gravitational constant, this nice number right here over here, the mass of the large body in a two-body system, so kind of the Earth would be this mass relative to a satellite, the specific mechanical energy, which we'll discuss a bit later, and r, the radius of an orbit. Now, armed with our knowledge about orbits, let's talk rocket science, specifically the Vis-Viva equation. We can model an energy system with an energy diagram, which shows the gravitational potential energy of an object becoming increasingly less negative, so it becomes greater, the farther away it is from the center of mass of the object, in our case the Earth, which is down here. However, if one is to be in orbit, they must also have kinetic energy as they'll be moving around the Earth. So we have our object in orbit over here, and this is the kinetic energy of the object on this diagram. This idea is expressed mathematically with the following formula, where we have the total energy is equal to the kinetic energy plus the gravitational potential energy. We can expand this formula into its component terms, but we need some more information to do something really useful with it. Another formula states that the velocity around the circular or elliptical object is approximately equal to 2 pi times this semi-major axis divided by the period. Then, Kepler's third law shows that the period is equal to 4 pi squared times the semi-major axis cubed over the standard gravitational parameter. Combining these two formulas, we get the velocity of an object in a circular orbit. Substituting this into our energy equation, we get that the kinetic energy plus the potential energy is equal to the negative of the gravitational constant multiplied by the m over 2 times the semi-major axis. I'll just refer to it as a from now on. And this is finally equal to epsilon, or the specific mechanical energy in orbit. We're not done yet, though. Setting the two equations equal to each other and doing some algebra, we get that the velocity at a certain point in the orbit is equal to the square root of the product of the standard gravitational parameter and the difference between 2 divided by your current radius of the current orbit you're in minus the 1 over the semi-major axis. Nice. We've got one of the two necessary equations to launch our rocket.
In order to build rockets, one needs to know how much fuel they need to put into their rocket to get their payload of mass x into orbit y. For this, we have the rocket equation, which has its humble foundation in the equations for momentum and force. The two momentums a rocket tends to experience are its own momentum and its fuels. The momentum of the rocket itself is equal to its instantaneous mass multiplied by the change in its velocity, whereas the fueled momentum is the negative mass exhausted multiplied by the exhaust velocity. This value is negative because our frame of reference is the rocket, relative to which the gas is moving backwards, and hence has a negative momentum, relatively speaking. Subsequently, the momentum of the system is the sum of these two. The force on the system consists of the pressure of the exhaust gases and gravity. This may be mathematically explained and shown with the following equation, where we have the exhaust pressure of the gas, the atmospheric pressure kind of going back in on the gas, the exhaust area, and finally gravity with the angle of the rocket. Knowing these two equations, we can go a step further and expand the formula by realizing that acceleration is actually the first derivative of velocity. With a bit of algebra, we get that F times t is equal to the mass times a change in velocity. Subsequently, the two equal each other, and we get that with a bit of rearranging, the product of the instantaneous mass and a change in velocity is equal to the pressure force exerted by the engine over a period of time dt plus the exhausted mass over the interval dt times the exhaust velocity. We get rid of gravity since it doesn't factor into the specific calculations that we use. And essentially what we get is we relate our change in momentum to our impulse and are able to rearrange the equation to make it in a more usable form. Given this relationship and that the mass flow rate, how much stuff is coming out of the rocket, is given with the density of the air in the combustion chamber, the volume of the combustion chamber and its area, and that dm is equal to the mass flow rate times the time interval dt, we can further rearrange the equation, this one over here, to get the following one over here. Then we introduce a new variable called equivalent velocity, which simply allows us to further perform another substitution into our main equation over here, further simplifying it. Conveniently, the mass flow rate per time interval dt is equal to the change in the instantaneous mass of the rocket. This is also a negative value since the rocket is losing mass as its fuel is consumed, as shown over here. With some more substitution and rearranging, we get that delta V is equal to the negative product of the equivalent velocity and change in instantaneous mass divided by the instantaneous mass. So the change over the actual. And now, finally, with this equation, we can get into some calculus. Firstly, we set up our equation so that it's in a form we can integrate by rearranging. Then we integrate and get that a change in velocity over a stage in the rocket is equal to the product of the negative equivalent velocity and negative natural log of the instantaneous mass. Now, before you start typing that I forgot to add the constant to the end of the evaluated indefinite integral, I'll let you know that this is actually a definite integral in disguise. To reveal its true nature, we've got to understand that a basic rocket has two masses. These are the masses of the empty rocket and of the propellant. And so the empty rocket is just the structure and the payload. Using the following equations, we may discern that the instantaneous final mass of the rocket is simply equal to the empty mass of the rocket. Now, combining this relation with our equation and rewriting the integral in this form, we get that the delta V is equal to the product of the negative equivalent velocity and the natural log of the instantaneous mass evaluated from the initial to the final mass. We can further simplify the natural log expression through log rules so that we get a ratio. But there's more. There's this little thing called specific impulse, or ISP, and it's equal to the equivalent velocity divided by the base acceleration due to gravity, or 9.81 meters per second squared in our case. Performing a final substitution gives us the rocket equation in its ultimate form. Hooray, we got it. There's some fireworks for celebration. So, armed with our two equations and knowledge of orbits, the time has come to tackle the mission head-on. The planet we'll be using today is Kerbin, an Earth analog in the spaceflight simulator Kerbal Space Program. It has a mass of about 5.3 times 10 to the 22 kilograms and a sidereal rotation period, or day length, of 21,549.425 seconds. Our goal is to launch the Calculus Relay satellite into a geostationary or keostationary orbit. We'll call this orbit KSO. Just for reference, a geostationary orbit means that a satellite's orbital period is equal to the length of the planet's day. Now, before we get off of the ground, we need to determine the Semimajor Axis and subsequent height of the orbit. We need to know this, since how can you get to a place without knowing where it is? Given we know the period of the orbit, since it's the length of the day, we can rearrange the period of a circular orbit equation, this one over here, to isolate for the Semimajor Axis, which is equal to the radius, and finally solve. And as a result, we get that the radius of the orbit from the center of Kerbin, the Earth analog, is 3,464,477.777 meters. And this is also equal to the Semimajor Axis, since this is a circular orbit. Now that we know where we're going, we need to figure out how much delta V we'll need to get there. To do this, we'll be using the Vis-Viva equation and the equation for calculating the Semimajor Axis. So these ones right here. The plan is to launch a rocket into a circular 100-kilometer orbit, then burn into a Bowman transfer orbit with its periapsis at 100,000 meters and apoapsis at 2,864,477.777 meters above sea level. In the calculations, as shown in this table which shows the steps, we have an extra 600,000 meters added to all of the orbits. As you can see here, instead of having 2,864,000 meters, we have 3,046 and 3,464. Simply because Kerbin's radius, the radius of the planet, is 600,000 meters. And since Kerbin is not a point object, we need to account for that extra when dealing with sea level as well as with our calculations. Now, in order to just to clarify before we get into it, this in terms of stages. So 0 stands for the final stage. This is with our satellite in its geostationary or keostationary, the KSO orbit. Whereas stage 4 is our initial stage. It is the fully fueled rocket at the launch pad at the launch center, called the Kerbal Space Center, or KSC. So in order to determine it, we have to go through a few steps. First of all, we have to find the orbital velocity of each circular orbit, so V0 and V2. Once we know the circular velocity of these orbits, we can start calculating our transfer orbits and the delta V required for them. Specifically, we need to calculate the orbital velocity at the apoapsis and periapsis of the transfer orbits. As you can see here, we have V1 apoapsis and V1 periapsis. This means that in order to get, for example, from our circular 100-kilometer orbit into the transfer orbit, which has its apoapsis at our required height, at the geostationary height, we need to burn from our from basically what we have over here. We have to burn from our orbital speed of what we have in our circular orbit, and we have to take the new orbital speed that we'll get from that burn. And so by finding the difference between the two terms, we're able to find how much delta V, how much velocity we need to gain in order to get from a circular orbit to this transfer orbit. And the same goes from 1 to 0, so from the transfer orbit to the circular orbit. In terms of stages 4 and 3, since both of these are slightly in the atmosphere, especially 4, we get only an approximation for how much we actually need, since we're going from 0 to essentially the circular orbit. and at the same time we have very complex models of atmospheric drag and the velocity of the rocket, which really complicated our approximations, and does not allow us to have an exact value. With our required delta V and final mass of our spacecraft known, we need to calculate the fuel required based on the engines we have in order to get the 3.211 tons to KSO. However, the spaceflight simulator is a bit restrictive, as it does not allow you to precisely tune the amount of fuel in your rocket, except by preset values. So, we are forced to stick with the values that we get, and by plugging them into the rocket equation, we get the actual delta V for each stage here. So we have the required and we have the actual. And this actual is simply calculated by taking the initial mass divided by the final mass, as in the ratio, taking the natural log, multiplying this by 9.81, and then by the ISP of the engine that we're using for that stage. Unfortunately, due to the restrictions of the game, we actually result in too little delta V by 20 meters per second in stage 1, and too much delta V by about 2 meters per second in stage 2. However, we do have a trick up our sleeves to counter this later on. As for stage 4, as explained previously, atmospheric drag and all of the various aspects of how density changes within the atmosphere, just simply due to how aerodynamics works, we're unable to have a precise and accurate measurement of how much delta V we need and counteract the drag to get off the ground. Now, having gone through all of this math and all of these physics, we are finally ready to launch the rocket. Awesome! Hooray! If you've made it this far, thank you for watching, and I really hope you enjoyed. And as promised, let's find out if Jeb survived.